Our discussion of uh, um, semiconductor materials. So let's go ahead with that. So what we want to discuss today is the concept of semiconductors, semiconductors and how they lead to electronic circuits. So we are not going to discuss everything today. We're going to get started with the concept of semiconductors first. But before that, let's start from slightly more basic material. So you might have all heard about semiconductors, but even though you know, let's start out with the concept of what is a conductor. So conductor. So conductor, so how do we know them? We know them as materials that are capable of conducting electricity. So that is what we know. So what do we mean by capable of conducting electricity? That means if you have a conducting wire, suppose like this, and you connect a voltage source to this wire, then a current starts flowing, right? So this is what we normally talk about, call a conductor. So this is what we normally visualize when we talk about a conductor. And good conductors, what are examples of good conductors? Good conductors are copper, which is the most common. All our wires are copper conductors. Then you have gold. Then you have silver. These are all good conductors. These are very good conductors. Okay. Uh, Now, what is it that makes them good conductors? So for that, we need to look at the atomic structure of these elements. So consider a copper atom, okay? So for copper, what is the atomic number of copper? Does anybody remember? In the periodic table?
29.
27.
29.
Yes, yes. So what it means is uh, the copper atom has 29 protons. So basically its atomic number that is 29. So what does it mean? It means that it has 29 protons in its nucleus, right? Nucleus. Okay. So what are protons? The protons are positive charge. Now, as we know, in order for an atom to exist, the number of positive charges by way of protons and the number of negative charges by way of electrons should match, right? So which means that there are 29 electrons as well, 29 electrons. Electrons orbiting the nucleus. Right? So this is what is happening. And how are these electrons? How are these electrons and protons distributed? So what you have is at the core you have 29. So these are negative charges. Electrons are negative. So you have 29 protons. So there's a 29 positive charge of 29 by way of protons. Then you have these cores. Then you have these orbits. So there's one orbit like this. Then there is another orbit like this. Then there's a third orbit like this. And then there is a fourth orbit like this. Okay. There are 4 orbits. Now, the first orbit has 2 electrons. So there are 2 electrons in the first orbit. The second orbit has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons in the second orbit. Then there are 18 electrons in this third orbit. So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 electrons in the third orbit. And then how many electrons we have so far? We have 2 plus 8 plus 18. 2 plus 8, 10, 10 plus 18, 28, plus 1 lone electron at the outer orbit. Okay, so there is a 1 lone electron. So this is the structure of a, this is the structure of a copper ion. So this is the structure of a copper ion. So, and then there is this 1 electron. So this electron is that. So you have 1 outer orbit. So what it means is that structure of a copper ion. So you have 1 single electron in the outermost orbit. This electron is actually the important entity when we talk about conduction. So this outermost orbit is also known as the valence orbit. Valence orbit. Okay. This is called the valence orbit. And then electrons in the valence orbit are known as valence electrons. These are known as valence electrons. So these are known as electrons in the valence orbits are known as valence electrons. So what happens is these electrons are put into place by this equality between the centripetal and centrifugal force. So this inner core, this 29 protons, they are attracting the electrons towards themselves, and then but then the electrons are moving, so they are creating a centrifugal force. So basically these two forces are matched, which means they are held on to their orbits. And then you can actually think of this. So from the perspective of the valence electrons alone, what you can think about is like this. So for a copper ion, so what you really have is a core of a net positive charge and a valence electron. So this is an alternative representation. So it's a valence electron. So this is a valence electron. And there is a core with +1 charge. Why +1 charge? What is the core? How do we define the core? So the core is nucleus plus all electrons except those in the valence orbit. Okay, so basically this is an alternative representation. So this is an alternative representation. So what's happening here is that in this particular representation, we are lumping together everything in here. So everything except the outermost core. So if you look at this figure, so we have all these things. You have one outermost core, the valence or outermost orbit, the valence orbit, and that orbit had this valence electron. That actually contributes to a -1 charge, and everything inside the 29 protons. We're not talking about neutrons because they are chargeless. So 29 protons and 28 electrons all together. What is their net charge? 29 protons and 28 electrons, which means 29 positive charge and 28 negative charge, which means you have a net positive charge in here. So you have a net. So if you look at this core, everything combined except for the valence electron, you have the net charge of +1. So you have a core with a net charge of +1, which actually consists of 29 protons plus 28 electrons. You have this core. And that core is, and then you have this valence electron. So essentially you can think of it as a core with +1 charge attracting a valence electron with a -1 charge. So that's the entire idea. Now, what happens is that this valence electron, this sole valence electron, is much outside than the other electrons, right? So the amount of attraction that this electron feels is not that great, especially as compared to these electrons that are towards inside the core. This valence electron is feeling a much lesser pull. What that means is that any outside force can rather easily knock off this electron. So knock off this electron from its orbit. So an outside force can dislodge the valence electron easily from its orbit. Now, when that happens, when some outside force dislodges the valence electron from its orbit, the dislodged electron is called a free electron. So basically, even without this, so I mean actually not the dislodged electron, and the electron that's on the outer edge is also actually called the free electron. So this is the valence electron. I'm sorry, because typical the typical definition is that the valence electron itself, the valence electron, which is capable of being dislodged very easily, is also referred to as a free electron. Okay, so this is referred to as a free electron. Why is it referred to as a free electron? It can be very easily discharged, and then it can hop from one positive core to the next. So basically, what happens is if you dislodge this electron, it can move from one atom to the next. So you can easily dislodge a lot of electrons, so the electrons can move in a direction. So this is why it's called the free electron, and this movement of electrons actually lead to the current. Okay, so because the easier it is to dislodge the valence electron, the better the conductor. And whenever you have just one free electron in the valence orbit or just one valence electron, these materials make for very good conductors. So materials with a single valence electron make for good conductors. All right, so that is so all these materials, so copper, silver, gold, all of these have one valence electron. So these are very good conductors. Okay, so that is that is about conductor. So, but what we are concerned about is not conductors but semiconductors. But now that we know conductors, what are semiconductors? Before the conductors, let's see what are insulators or the natural state of atoms. So natural, then that will talk about nature. So the natural state of atoms. So atoms try to have 8 valence electrons. So this is a property of nature. So this is a property of nature. So this is something that you can take as a hypothesis. That's a property of nature. So basically, this is so using advanced science, you could analyze these things. But the main point is, whenever you have a you have some atom, the most natural state of its being is to have 8 valence electrons. Okay, so that is something we will see. But materials with 8 valence electrons are good insulators. Okay, so with 8, because they don't tend to do anything. They're happy in their state. Valence electrons make for good insulators. Okay, so that is, but now let's go to the semiconductor. Semiconductors are somewhere between conductors and somewhere between say, conductors and insulators. So these are between conductors, somewhere between conductors and insulators. So you have perfect conductors, perfect insulators, then you have something between conductors and insulators. Now what happens with semiconductors? They have 4 valence electrons. So they're exactly in between 1 and 8, they have somewhere in between, they have 4 valence electrons. What are the examples? Examples. The most common example of semiconductor, can somebody tell what the most common example of a semiconductor is?
Germanium.
Silicon.
Yes,
Silicon.
yes. So silicon and germanium are the most common. These days, silicon is the most common. So, but initially in the early days, germanium was used as the preferred choice for semiconductors until some problems with germanium were discovered. But then silicon took its place. Silicon earlier had the problem of refining, how to refine silicon, that was a problem. But now that problem has been overcome. So what we have is silicon as probably the most common, silicon. Then you have germanium. Carbon is also, can also act as a semiconductor, okay? But carbon is used most for, in order to make resistors and all these things. But basically you have silicons, silicon and germanium. These are the most common semiconductors. All right, so all these things have the property that they have 4 valence electrons. So carbon, number 6, right? So 2 at the inner orbit, 4 electrons at the outer. Silicon, silicon again has a silicon also has the same. So silicon's number is 14. So basically what you have is you have 2, 8, 4. So there are 2 electrons at the core. So for example, if you draw a silicon atom, so what you have here is there is a positive charge of plus 14 here. Then you have 2 electrons here, not valence, 2 electrons here in the second orbit. Then you have 8 electrons in the second orbit, 1, 2, 3, 4, 5, 6, 7, 8. And then finally, at the outermost orbit, so I'm showing the core using solid lines, and then the outer valence orbit is, there will be 4. So 1, 2, 3, 4. So that is your silicon. So basically you have a silicon atom looking something like this. So you had 14 protons inside and the neutrons, and then you have these electrons. So just to make sure that when you get your notes, you know that these are all electrons. So basically these things, these are all negative charges. Basically these are all negative charges. So these are all electrons. Similarly, over here, you have these negative charges. So these are all electrons. So these are the valence electrons. So you have 4 valence. So it says silicon atom. It has 4 valence electrons. Okay. So basically you can think of this as a core with a net charge of 4. So in our alternative discussion or alternative definition, you can think of this as you have a core with net of 4 charge. So this is your core, and then you have this valence orbit with -1, -1, -1, and then a -1. Okay, so this is your alternative representation. All right, so now in reality, I mean in practice, in the real world, these things don't exist in isolation. These atoms cannot exist in isolation. So what they do is they form bonds. So from your studies before, prior studies, you already may know that atoms like silicon or carbon, these atoms form covalent bonds. So what does it mean? In covalent bonds, these atoms actually place themselves in an orderly pattern so that any two neighboring atoms share one electron. So basically you have four valence electrons. With each of these valence electrons, there will be associated another atom, nearby atom, and that would share another electron from there, another valence electron. So in effect, each of these atoms will have 8 valence electrons, out of which 4 would be shared by some other, 4 other atoms. So basically, what you see is covalent bond. So covalent bond, what happens is, so basically silicon atoms arrange themselves in a pattern which is called a crystal. So they will arrange themselves in a pattern called crystal. So in the crystal, what happens is each atom will have one. So if you think of a silicon atom, what will happen is you will have this is silicon, then it has a bond, it has an outer orbit, valence orbit. So that orbit, it will obviously have 4 valence electrons. So this atom will bond with another atom. So these are the cores. So these are the cores. So this core, and this guy will have obviously 3 other things. Then this one will bond with another atom. Okay. Then there will be another one here. This is a single atom. Okay. So that one will have 1, 2, 3, and finally this one will also be bonding with another atom. This is another 1, 2, 3. Okay, so basically what we are saying is that if you look at one atom, one central atom, for example, this atom, this particular atom, it has 4 neighbors, and from each neighbor, it borrows 1 electron. So this electron, these electrons, these shared electrons, these remain in their place in this orbit because they are pulled by both atoms in an equal and opposite direction, or with equal force in the opposite direction. So, for example, if you look at this atom, this electron, this is being pulled by this inner core and the outer core as well. So basically, it feels a pull in both directions, equal and opposite pull. So that's how it stays in its orbit. So basically, what happens in the crystal is every atom is surrounded by 4 other atoms, and then all those 4 atoms lend 1 electron each. So basically share 1 electron each with this central atom, which means you have 8 electrons in the valence bond. So this is a much more stable structure. So this is how all the atoms in a large number of millions of atoms, billions of atoms will get together and they'll form covalent bonds. And what you get at the end, that solid piece of material you see is a crystal. So that's a silicon crystal. So this sort of bond, so this is a covalent bond. So this type of bond is a covalent bond. All right, so this is basically a covalent bond as opposed to ionic bonds. But over here, we don't care about ionic bonds. We are really interested in covalent bonds. Okay, so now, as I said before, these 8 electrons provide a sort of chemical stability, which results in this solid piece of silicon material. So this particular reason, the particular reason why you have eight electrons in the valence bond to make the material stable, that is not a straightforward. Nobody has a straightforward answer to that, as the textbook says. And by the way, all these things that I'm discussing right now is straight from the textbook. So I urge you to read the textbook thoroughly, because this is very important. I hope everyone has done a copy of the textbook, because from now onwards we are going to follow the textbook in a rather detailed manner, and we'll follow it very closely, because so far we have been doing some sort of a review, but now onwards we're going to stick to the textbook in a much more closer manner than what we did in the first two lectures. Okay, so that's an aside. But anyway, coming back, so you have these 8 valence electrons, that gives it some sort of a stability. So what we say is that when you have 8 valence electrons, then we call that the valence orbit is saturated. So when the valence orbit has 8 valence electrons, we call it saturated. So it cannot accept any more electrons. So it does not want to take anything. It doesn't want to make it 9. Okay, so that is a common property of materials. So these valence orbits cannot hold any more. So it's already saturated. It has all 8 electrons, and these 8 electrons, these 8 electrons are called bound electrons. These are called bound electrons. Why are they called bound electrons? Because they are held very tightly by the atoms. So because they are held, you have this stable structure where you have 8 valence electrons which are held tightly by the atoms. They are stuck in their position because they are feeling this equivalent opposite pull from the 2 associated atoms, and then it's a so nobody, they don't want to change the structure, so they want to stay that way. They are happy in their place. So this is a this is a saturated valence orbital structure. So when you have that, the material acts as almost a perfect insulator. So in this state, the silicon crystal acts almost as a perfect insulator. Because you have this saturated state. Okay, so at room so in this state, insulator at room temperature. Because if you increase the temperature, something happens. So that's another matter. So at room temperature, this is what you expect that the silicon crystal is almost an insulator. So nothing can happen in this thing. So you put some voltage, some little bit of voltage across the silicon crystal, nothing will happen. It'll act like an insulator. Now, this room temperature is, so in addition to room temperature, let's define another word called ambient temperature. So room temperature is, what is room temperature? Room temperature is approximately 25 degrees Celsius. Some people call it 27, but the textbook says 25, so let's go to 25. So the ambient temperature, so you have this ambient temperature is the surrounding temperature. So temperature of the surrounding. So you have an ambient temperature, the temperature. So now when the ambient temperature, if the ambient temperature is greater than the absolute zero, so 0 Kelvin. So when if ambient temperature is greater than 0 degree Kelvin, that is minus 273 degrees centigrade, then what happens is that for the heat energy causes the silicon atoms to vibrate, and this has a and the higher the temperature, higher temperature leads to more vibration. Okay, so if you have higher temperature, then you have more vibration, and then vibration can occasionally dislodge an electron from its stable saturated orbit. Okay, occasionally dislodge an electron. So basically, it can dislodge an electron from the valence orbit. All right, so when that happens, so if you have a valence orbit is dislodged from the valence orbit, that means it becomes a free electron. So it becomes, a free electron. So just like a copper atom that we discussed, so you can have some occasional free electrons even in a silicon crystal, although it's almost like an insulator. It might still give rise to some free electrons, and these free electrons are just like the free electrons that you saw in the copper ion. And when you so departure of the electron, so departure or so dislodgement of the free electron leaves behind what is known as a hole. This thing is called a hole. So this is nothing but it's a vacancy in the valence orbit. So it has some place to basically you had a valence orbit with 8 electrons, and then suddenly 1 electron is dislodged. So what you have here is a vacancy for a single electron. So it's essentially, you can think of it as a net positive charge. Yes? Any questions? Okay, so maybe there was some noise, but anyway, so basically what happens is that you can dislodge 1 electron from the valence orbit, and that when that happens, you essentially have this vacancy for a single electron, and that entity, that valence electron with only 7 valence electrons, that is a hole. That is known as a hole, which means it is essentially effectively a net positive charge. So effectively a +1 charge. So this is, so what remains is basically a hole with a +1 charge. All right. So this can, so the hole can act as a positive +1 charge, and it can capture an electron. So a hole can capture a hole acts as a positive charge. And capture an electron. So it can capture an electron. So basically, what is a hole? This is an important word because you will come across this word hole very often. So the hole is nothing but if you have a structure with the saturated valence structure and you knock off 1 electron from that structure, what you get is a hole. That hole is effectively a net positive charge that has the capability to capture an electron. If it finds a free electron somewhere nearby, it has the capability of capturing the electron. Now, these holes and electrons, this particular structure is actually at the very core of electronics. So how do we deal with these holes? How do we actually create these holes at our will? and intentionally create holes at some place and intentionally create a lot of free electrons at some place. And then how do we make use of these structures? So that is what electronics is all about. So at least at the device level. So when you do the circuitry, it looks like an electrical circuit, but when you are actually going deeper into this electron to the device level, then you see that there is always some interplay of holes and free electrons going on. So how do we actually make use of holes and free electrons? How do we fuse them together? How do we fuse two pieces of material, one with a lot of holes and one with an excess of free electrons? How do we fuse them together and then make them do certain functions that a typical conductor or a typical insulator will not be able to do? So that is at the core of electronics engineering. So this is why this is this forms the basis of electronics. Okay, so now coming back, so what happens is that at room temperature, whatever temperature, so as I said, if you go back, so this dislodgement of electron, what knocks off the electron? It's heat. Now, the amount of heat you get in room temperature, that actually produces only a few holes and free electrons. That thermal energy at room temperature cannot produce a whole lot of free electrons and holes, which means the capability of the semiconductor to conduct a lot of current at room temperature is simply not present. So at room temperature, only a few holes and free electrons are created by thermal energy. Okay, so this is what this is an important thing. At room temperature, if you try to see how many holes and free electrons are being produced in the silicon crystal, that's not much. Now, in order to make use of these things as electronic components, we want a lot more than those. We don't want so few holes and free electrons. We need more than those, and we want to create them in a controlled manner. How do we do that? How do we create more holes and how do we create more free electrons? We do that by a technique called doping. So doping. So there is a technique called doping. So the doping is a procedure to increase the number of free electrons and holes in the silicon crystal. So I often refer to as silicon because these days we are normally dealing with silicon, but it could be germanium. This not necessarily silicon. I mean, anyway, you can dope a silicon crystal, you can dope a germanium crystal, but we are doping mostly as the silicon because that's what we use these days. Okay, so now that would be we will see these things. So, but what doping is? So doping is the procedure to do this. So doping involves adding impurity to the crystal. What are these impurities? As we will see, these impurities could be boron, aluminium, or phosphorus. So all these different types of impurities will lead to different sort of behavior. So sometimes you might want to increase the number of holes, sometimes you want to increase the number of electrons, and so actually what we want to do is we want to do both, and then we want to create crystals, one with create a piece of silicon with excess of free electrons, create another piece of silicon with excess of holes, and then we want to place them together. Basically, we want to have this single piece of silicon material. On one side you have an excess of holes, one side you have an excess of free electrons. So this is what we want to do, and this thing can be done by doping this part. So we do some sort of a doping on this side, and then we dope this side in order to get this desired concentration of holes and free electrons. And then this combined material with excess of holes on one side and the excess of electrons on the other side behaves in a certain manner, and that makes us that actually lays down the basis for all of electronics. Okay, so we will talk about these things, but there are some other concepts as well before we move on to doping. So one is so for the first thing we have to keep in mind is in a pure crystal, if you apply thermal energy, there will be holes and free electrons created, right? The number of holes will equal the number of free electrons, because every time you create a free electron, you leave behind a hole. So there will be a lot of free electrons, lot of holes, but the total number will equal one another. So total number of electrons would be total number of holes, and then these free electrons that would be generated would be moving around randomly. So you knock off one electron, it moves around randomly. Eventually, what happens is that it will find it'll find some hole and then combine with that. So basically, that part is called a recombination. So the main takeaway from here is that thermal energy creates equal number of holes and free electrons. Okay, free electrons. That's number one. And number two is recombination. Or before that, let's say these electrons, free electrons, move around randomly. Before merging into a hole. Merging into a hole. So this process is called the recombination. This process is called the recombination. So the definition of recombination is the merging of a free electron and the hole. And then finally we define that word called lifetime. What is the lifetime? So lifetime is the time between the creation and disappearance of a free electron. The time between the creation and disappearance of a free electron. All these definitions are there in the textbooks as well. So as I said, I'm trying to follow the textbook as closely as possible. So you please get hold of a copy if you haven't already and read the textbook because these things will be there as well. And it's explained in very good detail over there. So basically this lifetime can be of the order of microseconds or a few nanoseconds. So basically nanoseconds to microseconds. So how long can an electron exist, free electron exist before it merges with some other hole? That lifetime that is defined as lifetime, and that lifetime can range between nanoseconds to microseconds. Okay, so that is the range, that's the range of the lifetime, typical range of a free electron lifetime. So basically you can summarize this whole thing as whenever you have a crystal at some temperature higher than 0 degree Kelvin or minus 270 degree centigrade, there will be some free electrons and holes being created. So every time you create a free electron, there will be a hole created, and this is done because of happens because of thermal energy, because of heat. And then as these are created, some free electrons will recombine with some holes, and then free electron will create again the more free electrons will be created due to thermal energy, and they'll recombine. So this process goes on. However, at room temperature, this happens. You don't have a great deal of holes and free electrons. Okay, so that's the point to keep in mind, as I said before. But the important thing is the number of holes and the number of free electrons in this pure silicon crystal. This pure crystal is always the same. So if you have 1 million holes, then there will be 1 billion free electrons. So that is always a constant. That does not change. So we have to always keep in mind. So a pure silicon crystal has equal number of holes and free electrons. Free electrons. Okay, so this is something that's very important. All right. Now let's so this is the whole thing. So this pure silicon crystal. So what is the pure silicon crystal known as? We call it an intrinsic semiconductor. So an intrinsic semiconductor, a pure silicon crystal or a pure germanium crystal, is an intrinsic semiconductor. So basically, the term is intrinsic semiconductor. An intrinsic semiconductor is basically a pure semiconductor. It's a pure semiconductor, no other impurity present. So you get a piece of silicon, you refine it so well that there's nothing else is present, then it will be a intrinsic semiconductor. Do the same with a germanium. It'll be a intrinsic germanium semiconductor. The main point is no impurities. So no impurities. That's important. Impurities. All right. Now at room temperature, if you're looking at a silicon crystal at room temperature, intrinsic semiconductor at a room temperature, then there are so few holes and electrons being produced by thermal energy. It acts as almost an insulator. So at room temperature, or maybe acts as an insulator at room temperature. Why does it happen? Because you have only a few holes and electrons being produced. Because of too few holes and free electrons. Okay, so because the thermal energy at room temperature is not sufficient to create a lot of free electrons and accompanying holes, so you don't get good conductance. Now, how does it? But suppose you have these free electrons. So suppose you have a free electron in this in a silicon crystal. How does these electrons move, and what happens to the holes in this case? So basically, if you have a so if you suppose you have some sort of a silicon crystal, so this is again a figure from the textbook. So I would refer you to the textbook for a detailed and more better version of the figure. So what you do is you put you take two charge plates, and then you put some put a crystal in there. So you basically put a crystal in there. So these are all silicon atoms. So they should have been drawn in a much better manner. So refer to text, okay? Refer to textbook. Okay, so for this refer to textbook. But what we mean here is that if you take a silicon crystal, so this is a silicon crystal. So this is a silicon crystal, pure silicon crystal, and then I am connecting that crystal to the two plates of a battery. So one plate is creating a positive charge, there is another plate that's creating a negative charge. And then what happens? So whenever there's a free electron somewhere, that free electron will be pushed in the left direction by will be pushed in the direction of the left by this potential. So the external battery will be pushed to the left. And what happens to the holes? These holes will move in the opposite direction. So suppose there is a hole in here, and then there is a electron in here. So what happens is that the electrons, an electron, if it's at this position, it tries to move in the left direction and merge with a hole. But when it merges with a hole in this direction, at this point, suppose it merges with this hole, and it moves from here to here, that means at this point, the original location of the electron, there is a hole being produced, right? And then the same thing can happen on the other side. So basically, then because of this new hole being produced, another electron to the right of it might jump into this hole. So then this old hole will be balanced out because there is a new electron coming in. But then the old electron will leave a hole behind on the other side. So basically, what you have is the holes will move in this direction. The holes will move in this direction. The electrons, free electrons, in this direction. So free electrons will be moving to the left, and the holes will be moving to the right. So you can think of this whole thing as a movement of electrons only. So the holes are conceptual. So holes are not just moving, means jumping around. It's because there's a new hole created in a way so that if you look at that, it seems like the hole is moving from the left to the right, whereas the free electrons are moving from the right to the left because the whatever original free electrons are there, those are pushed to the left. And then these free electrons, once they reach this plate, so once the free electron reaches this plate, then it gets into the outside of this crystal because it's a conductor. So it jumps into this crystal and then it will merge with, or it will merge with the positive terminal of the battery, because the positive terminal of the battery is a positive charge and the electron is a negative charge. So it will be merging with that. And the holes will be moving in this direction, in the direction from left to right, and at some point it's going to encounter a negative charge pushed in by the battery, the negative electrons in the supplied by the battery, and then that hole will disappear. So this process continues. So basically what you have is you have you have some holes moving in the you have holes moving from left to right, and you have electrons moving from right to left. Okay, so this is the idea. And then one thing to keep in mind is that this electrons, whatever is there, that can jump out and then get into the battery on the semiconductor. The hole itself is just a concept. The hole will not move out of the crystal. So it's eventually going to recombine with some electron on the right end of this right end of the crystal, because right end means your negative end. So in the negative side of the battery, the negative side of the where the negative side of the battery is connected, it will be merging with an electron. The hole will be merging with an electron. So basically, the entire point is that these holes will be moving from the positive terminal to the negative terminal. The electrons will be moving from the negative terminal to the positive terminal. And then these electrons and the holes are often called carriers for this very reason. They are carrying the charge. So electrons and holes are called holes and free electrons. Electrons are called carriers. These are carriers because they carry charge from one place to the other. So basically, they are carrying, so the negative charges, the electrons are carrying their charge from from the left to the right, whereas the holes are carrying the charges, positive charges, from right to the from left to the electrons are from the right to left, and holes from left to right in this case, because from the positive to the negative. Okay, so that is the point. So basically, if you write this whole thing, so basically what we really have is you have some semiconductor device, and then so you have some semiconductor, and then you connect it to the positive terminal of a battery. So you have a flow of electrons in this direction and the flow of holes in this direction. Okay, so this is what this is how the semiconductor will behave. So this is not different from a conductor, right? So if you put a put this semiconductor, put a conductor, let's say a copper wire, the same thing will happen. There will be a flow of electrons in this direction. So this is what is happening in the semiconductor as well. So you basically have a flow of current in the direction of the potential supplied by the battery. So basically the electrons are moving in this direction. So the positive current, if you define current as the movement of positive charge, then the current is in the opposite direction. But either way is the same as a conductor. But the thing is, you'll not have too much charge moving, because the pure silicon, as I said, the pure silicon crystal does not have too many holes and electrons, so it cannot carry a lot of charge. To increase the conductivity, we need to dope the crystal. Conductivity of the semiconductor we need to dope the crystal. So we will need to dope the crystal, and as I said, doping is a process of adding impurities. So when you add impurities, when you add certain impurities, that will increase the concentration of either free electrons or holes. Okay, so there'll be an increase in the concentration of free electrons or holes, and that will lead to greater conductivity of the material. Because when you have more holes, you can get more positive charge flowing in a direction. Or if you have more free electrons, they will take you in the opposite direction. But the point is, if you just take a silicon crystal at the room temperature or even a slightly higher temperature, you don't have enough free charges that would be moving to give you the desired current. Whereas if you really want to use it as for some sort of conduction, you will have to dope the semiconductor by adding some impurity, and that would increase the concentration of either the positive or the negative charges. All right, so let's look at this question of doping. So how do we dope this thing? So if you dope it, so doping is the process of adding impurity. We'll see what impurities are added. Impurities to the semiconductor. And then the doped semiconductor is often called the extrinsic semiconductor. A doped semiconductor is called an extrinsic semiconductor. Because an extrinsic semiconductor is nothing but a doped semiconductor. Okay, so we now know what doping is. I mean, what is an extrinsic semiconductor? But what exactly is doping? What do we add? What sort of impurities do we add? So, what kind of impurity we will add depends on whether we want to increase our concentration of free electrons or we want to increase our concentration of holes. So, suppose we want to increase the concentration of free electrons. So, increasing free electrons. So if we want to increase the concentration of free electrons, then what we do is we dope the crystal with pentavalent atoms. What are pentavalent atoms? Pentavalent atoms are 5 valence electrons. So any atom that has 5 valence electrons. So if you have 5, so you can get an atom with 5 valence electrons that would make a pentavalent atom. And then if you dope the semiconductor with a pentavalent material, then you get a increase in the free electrons. How does it happen? We will see. But what are examples of pentavalent atoms? So 5 valence electrons. Example. So the examples, common examples are arsenic. Then you have antimony. And then phosphorus. Okay, so you have arsenic, antimony, and phosphorus. So these are pentavalent atoms. So all these have 5 valence electrons in the outermost orbit. Okay, so now what happens when you add a pentavalent atom? If you add a pentavalent atom, what happens is you take suppose you take a pentavalent atom. So this is some core 4 of a pentavalent atom, and then it has, so it will be sharing, so 4 of these atoms will be shared with 4 electrons, and then there will be 1 free electron. Why? Because this original pentavalent atom had 1, 2, 3, 4, and 5 electrons. Originally 5 electrons in this outermost orbit. Okay, so then the moment you add the silicon crystal, add this pentavalent atom, pentavalent material to the silicon crystal, 4 of its electrons will pair up with 4 other electrons from 4 silicon crystals. So basically you get these silicon crystals. So basically you have these silicon crystals. So this is your pentavalent atom. This is your pentavalent atom. You have these 4 silicon crystals. Sorry. You have these 4 silicon crystals. Just like before, you have the same atomic structure at the same covalent bond structure where 4 atoms are, there are 4 atoms being pairing up, 4 silicon atoms pairing up with the pentavalent atom. And then what happens is that you have already 8 valence electrons because of this pairing. So you have these 4 original electrons of the pentavalent atom, and then these silicon atoms are pairing up with this. And then you have total 8 valence electrons due to the pairing up of 4 silicon atoms. So one of the original valence electrons, so this particular electron, so this is silicon atom, silicon atom. So basically this electron is a free electron, becomes a free electron. This was originally a part of the pentavalent atom. So what happens here is that you take the pentavalent atom and then it gets 4 other electrons from 4 silicon atoms, and that way it makes up for 8 valence electrons. But there is 1 extra electron that came because it had originally 5 valence electrons. So that 5th valence electron becomes a free electron. So what happens after this adding the pentavalent impurity is that you have a crystal that has an excess of free electrons. So this time, if you notice, we didn't create a free electron at the expense of a hole. So earlier, whenever we created a free electron using thermal energy, we created that by knocking off 1 electron from a stable valence orbit of 8 valence electrons. So that way what happened was that we created a hole that had 1 net positive charge. In this case, on the other hand, what's happening is you are adding something from the outside, some impurity from the outside that had 5 electrons to share, and of those 5 electrons, 4 have already paired, leading to 8 valence electrons, a stable structure, and 1 extra electron that is just being thrown off to some outer orbit, and that particular valence electron becomes a free electron. Basically, that free electron, there is an excess of free electron in this doped crystal, which has been doped with pentavalent atoms. So basically, the pentavalent atom will donate an extra electron. So the amount of pentavalent atom you add, you get as many as many free electrons. So that's why pentavalent atoms are called donor impurities. So that's why not atoms and pentavalent materials. So basically the pentavalent materials are called donor impurities. So why donor? Because they donate electrons. So whenever you take a silicon crystal and add some phosphorus, arsenic or antimony, what you would get is an excess of free electrons. So this is how you create all these free electrons, by doping it with a pentavalent atom. So as a manufacturer, what you could do is you can control how much free electron you need. So if you need more free electrons, you add more pentavalent impurity, more donor impurity. If you need less free electrons, you let less donor impurity. So basically the amount of free electrons can be controlled. So amount of free electrons can be controlled by controlling the amount of donor impurity. All right, so this is how you dope a semiconductor using a pentavalent atom, and that leads to a higher concentration of free electrons, and that these free electrons are not created at the expense of creating a hole, corresponding hole. So that's very important, because otherwise, if I just need free electrons, I could just increase the temperature and try to knock off more and more free electrons. But the difference in this case is we are creating free electrons not by creating another hole, but by adding an impurity that had an excess of free electrons to begin with, excess of valence electrons to begin with. So that's the basic idea of doping a free electron with doping up semiconductor with an intention of increasing more free electrons. So then the other way is, if you want to increase the number of holes, what do you do in this case? So increasing the number of holes. So we might want to do the opposite. We actually do want to do the opposite, because both these are necessary in the long run. So increasing free electrons, increasing holes. So if you want to increase the number of holes, then what you do is dope with a trivalent impurity. So what is a trivalent impurity? A trivalent impurity has 3 valence electrons. So 3 valence electrons. So for a pentavalent you have 5. So trivalent, of course, it has 3 valence electrons. Now what happens? First of all, what are the examples? So examples are your aluminum, then boron, gallium. So these are your trivalent impurities. So these impurities have 3 valence electrons. So what happens when you try to add 3 valence electrons? So if you try to add 3 valence electrons, it will again be surrounded by 4 silicon atoms. Each of them will share one of its valence electron, but because the original atom had only 3 valence electrons, it will be short of 1 electron. So that way, it will essentially act as a hole, and it will look for another electron from somewhere else, another free electron from somewhere else. So basically, it will act as your a net positive charge. All right. So basically, when you try to when you have some sort of a hole, so let's draw it over here. So suppose you have some pentavalent atom, the core, and then you have a orbit over which you originally had 3 valence. So you had three valence electrons. So this is your trivalent atom. Now what happens is, when you put these impurities into the silicon crystal, there will be one silicon crystal like this, for example. This will share 2 electrons. This will have another 3 somewhere else. Then there will be another silicon crystal somewhere here, let's suppose. 1, 2, 3. So these are silicon. And then there will be another silicon crystal over here. This is just hanging around here, but it has nothing to share. I mean, the trivalent atom has nothing to share. So these are all silicon. Okay, so this is a silicon, this is a silicon, this is also a silicon. So these are all silicon, and this is some trivalent atom. So what happens here is that it gets 4 electrons from some silicons, from some sorry, another. So basically, it has another silicon. Sorry. So this is okay. Okay. So basically, what you have is it gets 4 electrons from 4 silicon atoms. Then it has 3 of its own valence electrons. So what you have is 4 plus 3, 7 valence electrons. So it now has 4 plus 3, 7 valence electrons. So what it means is it is short on 1 electron. So it is short on 1 electron, which means positive charge. It's basically positive, which means it's a hole. So basically what you get is, if you add a trivalent impurity, then the trivalent impurity and the silicon atoms tend to form these crystals over which the valence orbit, the outermost orbit of the trivalent atom has 7 valence electrons, including those shared by the silicon atom. So it's short on one valence electron, and that valence electron, so that part is a hole basically. So for example, you can think of this as a hole. So here is a hole. So basically there is a place for 1 extra electron. So you can think of this entire structure, this pentavalent atom along with this trivalent atom along with these accompanying silicon crystals, silicon atoms. The entire unit is basically short on 1 valence electron for the trivalent atom. So that means you can accept 1 atom, and that is why we can call it, you can think of it as a hole. So this entire thing is a hole. So that is how, by including trivalent atoms, you can create a hole. So this is the basic idea. So this is basically an impurity. A trivalent atom is an impurity that creates a hole by accepting some electrons from the silicon, silicon atoms, and having room for 1 extra electron. So this is why these things, these have a these are in a position to accept another electron from somewhere else. So this is why these are called acceptor impurities. Acceptor impurities. So these things, trivalent atoms, are called acceptor impurities or acceptor atoms. So these are donor impurities versus acceptor impurities. So this is the entire idea. So as our textbook says, how do you actually dope these things? So first of all, what they do is, what the manufacturer will do is, they'll somehow produce a pure crystal, and then depending on how many holes, what concentration of holes or what concentration of free electrons you want, you will add a required amount of either donor impurities or acceptor impurities. So that is the process. That is the fundamentally that is the process by which we would create a crystal with excessive free electrons or excessive holes. So that is the basic idea. So now question is, as I said before, if you're looking at the creation of electrons, free electrons and holes by way of thermal energy, you always got the same amount of electrons and holes. So that was true for an intrinsic semiconductor, where you increase the energy, increase the thermal energy, increase the heat, and then you get electrons. Over here, as I said before, that is not the case. This can be for the doped semiconductor. The situation would be such that there will be always an unbalance. So some things will be higher. Some one of these entities, either the holes or the free electrons, would be higher than the other. So that is, so one of the examples given in the textbook, which I'm going to just repeat for us, is this. So example, so one of the example problem given in the textbook is, so suppose you have a doped semiconductor. So suppose you have a doped semiconductor. So you have 10 billion silicon atoms doped with 15 million The first one is billion, this one is million pentavalent atoms. Okay. So suppose you have somehow been able to dope 10 billion silicon atoms with 15 million pentavalent atoms. And then assume that at ambient temperature 25 degrees centigrade, that is room temperature. Okay. So another question is, how many free electrons and holes are there? So this is the question. So if you have a piece of silicon crystal that had 10 billion silicon atoms, now you manage to dope that with 15 million pentavalent atoms, 15 million pentavalent atoms, pentavalent atoms at an ambient temperature 25 degree, at a room temperature. Now the question they are asking is, how many free electrons and holes are there in this particular semiconductor crystal? So the answer is, so does anybody have any answer to this?
15 million.
Yeah, so basically, however many pentavalent atoms would be there, that many free electrons would be there. Because each pentavalent atom is a donor atom. So it donates one, free electron. So if you add 15 million pentavalent atoms, then you have 15 million free electrons. So 15 million free electrons. So this is the situation, 15 million free electrons. Okay, so this is because of 15 million pentavalent atoms. Pentavalent atoms. Okay, so this is the case. Now, how many holes are there? So that's a question. So how many holes would be there? Well, but in comparison to this 15 million free electrons, there are hardly any holes. You could think of approximately 0 holes. Or maybe not say approximately 0, but a few holes. We'll just say that only a few holes, and those were by the ones that were produced by thermal energy. Thermal energy, that is heat. So what we're seeing here is that if you take a semiconductor, silicon semiconductor with 10 billion silicon atoms, and then you add some then you add some pentavalent impurity, what happens in there is you get 15 million free electrons. And then there are no holes being contributed by those pentavalent atoms. They are not doing anything. So any holes that there are in this crystal, that you see in this crystal, would be those created by the heat energy. But that heat energy, as you can see, I mean, that particular heat energy is not sufficient to create a lot of holes. So that means in comparison with the 15 million free electrons, there's hardly any holes. And of course, whatever few holes are there, 100, 200, 1000, those will always be accompanied by a free electron. So basically, when we say 15 million free electrons, actually 15 million free electrons plus some very small amount of free electrons created by thermal energy. So these 15 million are created by the doping process, and then there will be a few more created by thermal energy by knocking off electrons. So that is one set of that is the situation with free electrons here, and the situation with holes is such that there are very few holes. Why? Because at room temperature, we are dealing with room temperature. There is hardly any holes being produced by thermal energy. So this is how you can control the amount of free electrons you want in a crystal. So if you are able to control the ratio of the impurity to the pure crystal, then you know how many what fraction of the material will contain free electrons. So basically, how many free electrons will be produced. So if you know for sure that this has this many pure crystal atoms, then you add a certain amount of pentavalent atoms so that you get exactly the amount of free electrons you want. And you could do the opposite as well. So if you, instead of these 15 million pentavalent atoms, suppose I have 15 million aluminum atoms. So these are all trivalent atoms. So in that case, what would happen is you will have 15 million holes and very few free electrons. So this is how you create the type of semiconductor you want. Now so basically let's define these things. So let's define two types of semiconductors. So extrinsic semiconductors, and these are of course extrinsic semiconductors. Semiconductors are defined as either N-type semiconductors or P-type semiconductors. P-type semiconductors. What is an N-type semiconductor? An N-type semiconductor is the one that we are talking about just now. An N-type semiconductor is a semiconductor where you have doped a silicon crystal with pentavalent impurity. So N-type semiconductors, N-type is silicon crystal doped with pentavalent impurity. So as a result, N-type semiconductor, so this is N-type, this is silicon crystal. So what happens here is, this is excess of free electrons. So this is negative charge, negative charges, excess of the negative charge. That is why N-type, that the word N comes because of this. Okay, so the negative charges, because it has a lot of negative charges in here, so that's why we call it an N-type semiconductor. Okay, and then the free electrons. So the free electrons are majority. So basically, free electrons are the majority here. Holes are minority. So that is why we call the free electrons, term them as majority carriers. So if you want to carry some current through this, you are going to rely on the free electrons, right? So basically these free electrons would be the majority carrier. These are called the majority carrier, and holes are called the minority carriers. Minority carrier. Okay, so this is why this is the definition of an N-type semiconductor. So so what would you do? What happens here is that to get an N-type semiconductor, you take a silicon crystal and dope it with a pentavalent impurity. Now next is the P-type semiconductor. So P-type is just the opposite. So P-type semiconductor is a silicon crystal. Normally we are talking about silicon these days, silicon crystal instead of germanium, but anyway, silicon crystal doped with a trivalent impurity. Right, so this is a silicon crystal doped with a trivalent impurity. And so what you have is, you have an excess of holes. Excess of holes. So that's why, so the positive. These are positive charges, that's why P-type. That's why P-type. So N and P is just negative, positive. So if you see N-type, that means there's a lot of negative charge. Where does negative charge come from? Negative charge comes from electrons. So that's why you can immediately say that this is a N-type semiconductor, has an excess of free electrons. So in order to, and the only way you can get an excess of free electrons is by doping it with a pentavalent impurity. So an N-type semiconductor has been doped with and the pentavalent impurity, whereas for the P-type semiconductor, you have excess of holes, and excess of holes can come from doping with a trivalent impurity. So you can immediately say that, okay, it's a P-type semiconductor, that means it has either aluminum, boron, or gallium in there. Okay, so it's trivalent atom in there, trivalent impurity in there. Okay, so now this is the silicon crystal doped, then you have the excess of holes. And in this case, holes are called majority carriers. Majority carrier. And the free electrons are called minority carriers. So this is how we come up with this p-type and n-type. All right, so basically all we are trying to do is getting a semiconductor with a larger concentration of electrons or holes as we want to, depending on our wish, how we want to get them. Now the question is, why are we doing all these things? Is there any benefit to doing these things? Because if you, regardless of whether there is a hole, whether there is a excess of free electrons or whether there is excess of holes, how does it matter when you are trying to think of it as some sort of a conductor? You take some, suppose you take a n-type semiconductor, lots of electrons in there, and then you push a current in here. Okay, so you can think of okay, let's make it positive. So so basically what will happen is that the positive terminal the negative terminal of the battery will push through these electrons in this direction. These electrons will move in this direction, and then they'll move. And you can, the same thing you can conceptualize if you have a p-type semiconductor. Then you have all these positive charges in there, and then you connect a battery, the same battery here. So again, the positive charges will be moving in this direction. So the positive charges will be moving in this direction. Either way, you are getting a current. So either way you're getting a current. So what is it actually exactly doing? What purpose is it serving? So the point is, if you're just looking at a n-type or p-type semiconductor in isolation, these are actually not very useful in isolation. They are just like some sort of a resistor. So the electrons will, so if you supply a voltage, there will be some electrons moving through this entire through this entity, and that electron flow will give you a current. So just like any resistor, you get a resistor which will be made of carbon, for example, and then you connect it to a voltage source, as you have done in your first experiment, I guess, already in your basic electronics or electrical courses. So then there will be a current flowing through it. So what exactly is the benefit of doing all this, taking all the trouble of taking a pure crystal and adding silicon impure, adding either pentavalent or trivalent impurity? Well, the
Hello,
actual,
sir.
yes,
Hello.
yes. Any questions?
Yes, sir. Could you explain these parts again?
From which part would you like for me to explain again? So this conduction of current. Okay, so let me go back to this thing then. So as I said, you have these n-type and p-type semiconductors. One of them has an excess of electrons, the other one has an excess of holes. So either way, if you take this semiconductor and connect a voltage source across that semiconductor device, what will happen is that there will be charges flowing. So in one case, it will be the electrons flowing in a direction from the negative terminal to the positive terminal of the battery. In the other one, you have these holes moving. Actually, holes moving is nothing but they are actually pulling out electron, extracting electron from the neighboring atom, and so on and so forth. But at a conceptual level, all that happens is you have charges flowing from one point to the other. No difference. So you have a, just like the n-type, similar to the p-type, you get a current moving through this, current flowing through this circuit. So what exactly is the benefit? I mean, this is just like a resistor. So you get a carbon resistor somewhere, and then plug it across some voltage source, and there will be a current flowing. So the point here is, if you really want to make use of these semiconductors, what really becomes useful is when you take two semiconductors, one p-type and one n-type, and fuse them together. Okay, so the real benefit is over there. So what you really do is you take this semiconductor and somehow make sure that you dope one part make one part p-type. So you make one, this is a p-type, so, and then you dope the other half of the semiconductor using pentavalent. So this is you have this excess of electron. So there's a way to do this. I mean, manufacturers do this all the time. So what they do is they'll take a silicon crystal and then dope one part of it, one half of it, using some trivalent material so that you get a p-type semiconductor for that half, and they'll dope the other part with a pentavalent material, so that pentavalent impurity or donor impurity, so that they will get an n-type they'll get an n-type semiconductor. So these two things, which share this common boundary, common physical boundary, this thing together is actually forming the basis of electronic devices. So this junction, so if you do this, this junction is called the p-n junction. We will see why this is important. But the point over here is that at this point, what you really have is you have a silicon crystal. One part of that has been doped with a trivalent impurity, giving rise to a p-type semiconductor. The other half is doped with a pentavalent impurity, giving rise to an n-type semiconductor. And the junction between them, this is a physical part. So this junction, this physical entity, this junction is known as a p-n junction, because it is a junction between a p-type and the n-type. And this thing, this sort of arrangement is known as a diode. So this thing is called the diode. So diode is actually concatenation of two electrodes. So two electrodes. So basically two electrodes. So this is where this term comes from. Two is di. So di. So diodes. So these things together combined, you get diodes. Okay. So basically, what you are trying to do is you have in effect, you have a single piece of semiconductor, but half of it is a p-type semiconductor, excess of positive charge. The other half is an excess of negative charge because it's an n-type semiconductor. So what you can think of it as two electrodes fused together. So that's why you call it a diode. So, and this type of diode is also called a junction diode. So this is also referred to as a junction diode, also called junction diode or p-n junction diode. So these are all terms, but they mean the same thing. Essentially, what is a diode? A diode is a piece of semiconductor material, one half of which has been made p-type and the other half is of n-type. And the junction that's in between them, that's called the p-n junction. So this sort of arrangement actually gives rise to certain electrical properties that you cannot achieve in a pure conductor. So you cannot do all way around with these p-type, n-type arrangements with, for example, with a copper piece of copper. Okay, so this is why a diode is, and then this diode actually gives this entire entity some directional properties, as we will see in the next class. So today we are not going to get into the functioning of that. I just wanted to introduce what a diode is. So basically, diode is a semiconductor over which one half of is a p-type semiconductor, the other half is an n-type semiconductor. You can manufacture this sort of things in the industry. People have been doing it in a mass scale for a long time now. But this particular setup, this very simple thing, a connection of a p-type and an n-type material, that forms the basis of electronics. And this is actually so influential. This thing is so very consequential that everything you see today, starting from your laptop, cell phone to some rockets being launched into space, everything has this sort of somewhere you'll find this sort of material. So there will always be some role being played by this p-n junction. So this p-type and n-type is a revolutionary concept. So if you have this, then immediately you can do a whole lot of things that you could not have done with traditional materials that we knew before these semiconductor materials were discovered. But and then but for all that, the starting point is this p-type and n-type, this junction of p-type and n-type. And we will study in detail the properties of this diode, how it behaves, how it conducts electricity, in which direction it can conduct electricity. So these are important because this diode, as we will see, it has some directional behavior. You could, so in one direction current flows, the other direction it doesn't. In one direction current flows, but only after you provide a certain voltage or input. So if you connect a voltage source across a diode, the voltage has to exceed some value in order for some current to flow. So all these things are peculiarities of diodes, and these peculiarities actually make them very useful. Because otherwise, if this peculiarity was not there, if you just have a p-type semiconductor, let's suppose you don't have the n-type, just p-type, and you connect it across a voltage source, all you get is behavior that's very similar to a resistor. You supply a current voltage, you get some current, and then there will be some relationship between the current and voltage. That's done. But the moment you add these p-type and n-type, then the behavior completely changes. And that is what electronics is all about. So that is where we will start in our study of diodes. But today we are not going to get in there because we would be we are out of time, and I wanted to give you some time to process all this. So essentially, what we studied today was we started out with the idea of conductors. We said that conductors are those materials that have preferably just a single valence electron, that is an electron at this outer orbit, and the weaker the force that is attracting the valence electron towards the core, the better it is in terms of its conduction behavior. So the valence electron, the sole valence electron is not pulled in by a very great amount of force by the core. That is why it's very easy to dislodge that electron. It's very easy to knock off that electron, and that electron conducts. So that is what happens in a perfect good conductor. In a insulator, on the other hand, you'll see 8 valence electrons on the outside. But in the case of a semiconductor, it's somewhere in between. You'll see 4 valence electrons at the outside, at the outermost orbit. And then examples of semiconductors were silicon, germanium, carbon, etc. And of this, silicon is the one with most interest. That is most interesting to us. So in these electrons, we said that there's a covalent bond being formed by these things. And then each silicon atom tries to get 8 valence electrons in its outer orbit. So when it's in that state, we call it saturated. But even in a saturated case situation, you can make use of thermal to knock off one electron, and that would give rise to a free electron and that accompanying hole. A hole is nothing but a positive charge. And now these free electrons can conduct current, but the point is at room temperature, there are not too many holes and free electrons. Okay, so if there are a lot of free holes and free electrons, you could use this as a nice conductor, but that's not the case. So they will act for almost like an insulator at room temperature, these semiconductor materials, pure semiconductor materials. Now, in order to actually increase the number of free electrons and the number of holes, you could use a process called doping. So doping is nothing but you take a pure crystal and you add some impurity in there. Now, depending on whether the impurity is trivalent or pentavalent, that is, whether it has 3 valence electrons or 5 valence electrons at its outermost orbit, you get either a doped semiconductor with an excess of electrons or an excess of holes. If it is an excess of electrons, then we call it a n-type semiconductor. If it is an excess of holes, we call it a p-type semiconductor. And then finally, we saw that if you just take a p-type semiconductor or an n-type semiconductor in isolation and try to connect it to a voltage source, you will see a behavior very similar to a resistor. You supply some voltage, you get some current, that's all. No variations, nothing. No, I mean, there's no interesting variations in there. But the moment you take a p-type and n-type together and fuse them together, and then we claim today, we did not discuss this today, but as we claim, then you will see some interesting behavior of this particular piece of semiconductor material. And this piece of semiconductor material, where you have a p-type and the n-type parts fused together, that is called a p-n junction diode, or a junction diode, or simply a diode. So the term diode comes from 2 electrodes. Di means 2 electrodes. The odes of electrodes is there. So basically you have diodes. And then in the next class onwards, we are going to delve deeper into the operations of diodes, how they work, what happens, how these electrons are conducted through this barrier of this p-n junction, how do they cross the junction, how the current voltage characteristic of a diode look like, and how we can implement certain functionalities of certain interesting circuits using diodes. So that is the agenda for the rest of the week. Okay, so this is our discussion for today. So let's stop here, and then we will continue from the next class. Okay, and